hope everybody else did as well, and especially to Jose, who really, really worked really hard. Thank you, Jose. I'd like to present Rick Schoen, our last speaker of this meeting. I'd like to say just a few words to introduce Rick. Some of us have the good fortune to prove a really good theorem in our career, and we know it's a good theorem, and most mathematicians agree with us if we're really lucky. And sometimes these theorems are really useful for other mathematics. It's not always the case, it's very rarely the case. Sometimes you prove a really good theorem, and just it's 10 years later, it hasn't been mentioned, it's there, and 20 years later, it's still there. Rick proves really, really good theorems consistently, and almost consistently, these theorems are used by all of us. It's incredible that almost every paper that I write in the subject now, I'm using curvature estimates of Rick, or I'm using some unicity theorem of Rick, or some idea of Rick. And I'm sure that's true of all of us who work in the field, minimal surface theory and geometric analysis. Okay, so that's presentation. Thank you.
Okay, well, thank you for the very nice introduction, Harold. I'd also like to add my thanks to Jose, because I know that I asked him for several things, and he actually answered my emails and did everything. So thank you very much. And it's really great to be back in IMPA. I always really enjoy visiting here. And you know, it's good to be at the meeting. And I'd also like to congratulate Harold on his birthday. I met Harold in the early 80s, just as he was starting to work in this field. And it's really amazing what he's done since then. He's created the French School of Minimal Surfaces, and now is having a big impact in Brazil as well. Let me just say that in addition to proving really great theorems, Harold adds a human touch to the field, and is always very welcoming to not only to senior people, but also to students. And so it's a really I think that's the reason that he's been so successful in managing the field. In any case, I wish you a happy birthday and many years of productive activity to come. I'm going to give a lecture on Steklov eigenvalues and free boundary minimal surfaces. And I don't, a lot of what I'm going to say, the new stuff is not due to me so much, but I will at the end summarize results that are a few years old. But I wanted to, because recently in the last 2 or 3 years, there's been a flurry of activity just on the eigenvalue problem. And so I thought I would give a survey of some of those results. And some of them I think will be interesting also from the geometric point of view for those who are interested in free boundary minimal surfaces. And so I'm going to start just by introducing the problem. And then I'm going to, on part 2, I'm going to survey some bounds on eigenvalues that many of them have been done quite recently. And then in part 3, I'll talk about the extremal problem and the connection to free boundary minimal surfaces. So the eigenvalue problem that we're interested in is the spectrum of the Dirichlet to Neumann map. And so you just recall what that is. If you take a Riemannian manifold with boundary, then given, so the operator is an operator that acts on functions on the boundary. And so if I take a function, let's say it's smooth on the boundary, and then I can take its harmonic extension. So I just solve the Dirichlet problem. So U is the Dirichlet data for U hat. And then the map is the map that takes U to the normal derivative of U hat. That's called the Dirichlet to Neumann map. And it's actually a self-adjoint operator, and it's non-negative definite. And that just follows from Green's formula. So if we take U LV minus VLU, that's LV, remember, is the normal derivative of V hat. Then by Green's formula, that can be written as the interior term of U hat Laplacian V hat minus V hat Laplacian U hat. And that's 0 because the hats are harmonic. And so that shows that it's self-adjoint. And moreover, it's non-negative definite because if I compute the integral of u LU, then that's just the Dirichlet integral of the harmonic extension. Okay, and so it has a discrete spectrum because of Sobolev space theory. So there's if we take W12 functions on M, then the trace embedding goes into LP, and it's bounded up to this critical exponent, and it's compact for P less than that. So in particular, for P equals 2, it's a compact embedding, and so that means that we can diagonalize the quadratic form, which is the Dirichlet integral, on the unit sphere in L2 of the boundary, and then we can construct eigenvalues. I'll call them sigmas, sigma 0, sigma 1, et cetera, and orthonormal eigenfunctions form an orthonormal basis on the boundary. And so the eigenfunctions satisfy the condition that they're harmonic inside M, and their normal derivative on the boundary is proportional to the value on the boundary. And so the proportionality constant is the eigenvalue, sigma j. Okay, and notice there's a trivial eigenvalue, which comes from choosing the constant function on the boundary. Then the harmonic extension is a constant, and so that's in the null space, the kernel. So I've called it sigma 0 because it's 0, and then sigma 1 is the first positive eigenvalue. Okay, and there's a variational characterization, which is quite useful in application. So they're critical points of the Dirichlet form on M, but normalized by the L2 norm on the boundary of M. So if I took the L2 norm on M, that would be the Rayleigh quotient for the Neumann eigenvalue problem. That here we're integrating over the boundary. And so the critical points of this ratio in W12 are precisely the eigenfunctions. And there's the min-max characterization. So the kth eigenvalue is characterized as the minimum of the Rayleigh quotient, where I take functions orthogonal to the first k minus 1. So the eigenvalues can be constructed, and eigenfunctions can be constructed inductively in the usual way. Okay, and so they're smooth functions up to the boundary, assuming M and its boundary are smooth. And so let me give a couple of examples. So in some ways, the Steklov spectrum is simpler than the Dirichlet or Neumann spectrum. For example, if we take the unit ball, Bn in Rn, then the Steklov eigenvalues are simply the non-negative integers. And the eigenfunctions are just the homogeneous harmonic polynomials of degree k. So those satisfy their harmonic inside, and because they're homogeneous, when we take the radial derivative on the unit sphere, that's just k times the eigenfunction. And so in particular, unlike the Dirichlet or Neumann eigenvalue problem, where the eigenfunctions involve Bessel functions, special functions, in this case, the eigenfunctions are explicit, and they're simply the eigenfunctions of the unit sphere extended. And so that same idea works generally for cone manifolds. So if we take a compact manifold M0 and we take the cone over it, so we cross it with 0, 1, and we take the cone metric, so the origin then gets collapsed to a point. Then the same thing is true. The Steklov eigenfunctions are just homogeneous extensions of the eigenfunctions on the boundary with the unique homogeneity which make them harmonic inside and bounded at the origin, and 0 at the origin, actually. So in this sense, the Steklov problem includes the eigenfunction or eigenvalue problem for compact manifolds. So you could sort of embed the problem for compact manifolds into the Steklov problem in this way. Okay, so the cone, of course, is singular at the origin, but it doesn't really affect the analysis. So you can still carry it out with a mild singularity. Okay, and so let me mention, so the first basic bound which actually got started on this problem is a theorem that goes back to 1954 by Weinstock. And so what Weinstock proved is that if you take a simply connected domain in the plane, then he proved the sharp upper bound. And he proved sigma 1 of omega is bounded by 2 pi divided by the boundary length. So it's the length of the boundary. And equality is achieved only if the domain is a disk. And so in other words, another way to say it is that among all simply connected domains with a fixed boundary length, the disk has the largest sigma 1. Okay, that's the Weinstock theorem. And let me just give a quick sketch because it'll be the method is quite familiar by now to a lot of people because it was used about 15 years later by Hirsch in proving a result for metrics on S2. And so the idea is to use the Riemann map. So there's a conformal map, diffeomorphism from, well, so M is our domain. It could be any simply connected surface, actually, with a metric. And so there's a conformal map to the disk. And by composing with automorphisms of the disk, we can balance it. So that means, in this case, we take the center of mass of the map to be 0 around the boundary. So we use the arc length measure from M, the domain, and we can find a conformal transformation of the disk which balances the map. And then once these are balanced, they integrate to 0 on the boundary, so we can use the variational characterization of sigma 1. So in particular, sigma 1 is less than or equal to the ratio, and I've just brought the denominator to the left. And the Dirichlet integral in this case, the function's already harmonic, so it's just the Dirichlet integral of phi. And so if we add those up over the I goes from 1 to 2, then this is integrated on the boundary, and the boundary goes to the unit circle. So the sum there is 1 pointwise. And the right-hand side is now just the energy of the map. But the map is conformal, so the energy is twice the area. Okay? And so you directly get sigma 1 times the length is bounded by 2 times the, so twice the area of the image. The image is the disk, and so it has area pi. And so we get immediately sigma 1 times L is less than or equal to 2 pi. Okay, and so you might then ask, well, that's a beautiful proof, but on the other hand, it's very, very special because it uses the Riemann map. And so the question is, does the inequality generalize in a sharp form to higher dimensions or to other domains even in R2? And actually, there is a generalization for domains in Rn. And this was a theorem of Brock from 2001. So it proves a weaker but sharp upper bound for arbitrary bounded domains in Rn, in particular higher domains of higher connectivity in R2. And that's the inequality that sigma 1 of a domain is bounded by sigma 1 of omega star, where omega star is a ball with the same volume as that of omega. So in other words, inequality, again, holds if and only if omega is a ball. So in other words, what it says is that among all domains of a given enclosed volume, the ball maximizes sigma 1. Okay, and so that works for Euclidean domains. It's a rather, but it works for in all dimensions. And so let me point out, in the two-dimensional case, this is a weaker inequality than Weinstock's because what it says is that, if you just compute the number there, it says sigma 1 omega is bounded by the square root of pi times the area to the minus a half. And then if you use the Weinstock bound and apply the isoparametric inequality, you'll see that it implies this one. Okay? And so the Weinstock bound involves the normalizing the length of the boundary. The Brock bound involves the area of the interior, the volume of the interior. Okay, and so let me just say, so that the Brock inequality is true very generally, but it's actually quite straightforward to construct annuli which violate the Weinstock estimate. You can just take a disk and remove a very small disk centered at the origin, and you can then explicitly compute the eigenvalue, and you can see that it actually is bigger for a small disk. Sigma 1 times the length increases when you take a very small radius. And so in particular, the Weinstock estimate does not generalize to domains with other topologies. However, there is a coarse upper bound which works for any surface, say oriented surface with boundary. And so if we take a surface with boundary of genus gamma and k boundary components, then there's an upper bound which is actually, there are two upper bounds, and I've just used both of them here. One was in my first paper with Fraser on this, and the other is an observation of Kokorev. So the bounds are, the first one is 2 pi times the sum, gamma plus k, and the second one is a bigger constant, 8 pi, and then times the genus, this is the integer part of gamma plus 3 over 2. Okay, and so in various cases, either of these bounds may be sharper. The advantage of the second one is that it doesn't depend on k. There's no k dependence there, so it's independent of the number of boundary components. It depends only on the only on the genus. And actually, we also proved that the inequality here is strict, at least in the genus 0 case. K is bigger than 1. It's a sort of not a difficult nodal set argument to prove that the bound cannot be achieved. And actually, the second bound is never achieved. It turns out it's not possible. But the first bound, of course, is achieved in the Weinstock case. That's genus 0 with one boundary component, and that's 2 pi. But that's the only case for genus 0 in which it's achieved. We actually don't know for higher genus whether it might be a sharp bound or not in some cases. I mean, I expect it's not, but okay. And so I want to, as I say, I want to survey a few results. So these are very general upper bounds on sigma 1 times the length, which depend only on the topology of the surface. Now, if you look for lower bounds on sigma 1, then the geometry enters very strongly. In fact, there's a classical lower bound, which was due to Payne, Larry Payne, in 1970. And so he proved for a convex plane domain that sigma 1 is bounded by the minimum curvature on the boundary. And so notice, if it were the disk, then the minimum curvature would be 1, and the bound is actually sharp. So sigma 1 of the disk is 1. So that's a sharp bound, and equality is achieved only for the disk. And actually, this was generalized by Jose Escobar, who was at least partially from IMPA. In the late 70s, he worked on Steklov eigenvalue problems, and he generalized this sharp bound to surfaces with non-negative Gauss curvature. So remember, the upper bounds the bounds didn't depend on curvatures at all. They were just depended on topologies. The lower bound requires the geometric assumption of non-negative Gauss curvature and convex boundary, and then he proved the same result. He also extended it to higher dimensions, assuming convex boundary, and he was able to prove that sigma 1 is bigger than 1/2 kappa min, where this is inside the metric is non-negative Ricci, and kappa min is the smallest principal curvature on the boundary. And actually, he conjectured that this constant 1/2 should be a 1. Then it would be a sharp bound for domains in Rn as well. But as far as I know, that hasn't been proven in higher dimensions, the constant being a 1. Okay, and so there's another thing that Escobar was looking for in the late 90s when he was working on this was a kind of analog of the Cheeger inequality for eigenvalues. You know, there's the Cheeger inequality typically takes the form, for a Dirichlet or Neumann problem, bigger than or equal to 1/4 times h squared, where h is an isoparametric constant. It's different for the two. Quantity. And in fact, it's a lot less clear how to do that for the Steklov problem because, I mean, it basically follows from the isoparametric quantity is a kind of an L1 Poincare inequality, and then you can go from L1 to L2 just using really the Schwarz inequality. And so he was looking for it. In fact, he had a partial result of that type. Well, just this year, a French mathematician, Pierre Jahm, found an isoparametric lower bound, and it's rather interesting. So he proved that sigma 1 is bounded by a product of two isoparametric constants over 4, where the first one, so the picture here is you take your manifold and you divide it in 2 by some region, and D is the domain of smaller volume, and then the boundary of D has 2 parts. There's an interior boundary and there's an exterior boundary. And the first inequality is just the infimum over such subdivisions of the manifold of the ratio of the volume of the interior boundary divided by the volume of the domain. And that's actually the same, that's actually the Neumann isoparametric quantity. Okay, and so that gives a lower bound on the Neumann problem. And the H prime of M is the infimum of the ratio over the interior boundary divided by the exterior boundary. Again, over all domains where you look at the one of smaller area. And he proved actually the argument's pretty straightforward. He proved that sigma 1 is bounded below by this quantity. So it's a rather interesting sort of the advantage of isoparametric quantities that you can visualize them much more easily. So you can give you can sometimes compute them much more easily. Okay, and so that's a very recent work. The paper appeared a few months ago, as I said. Let me mention, so we talked about upper bounds on the first Steklov eigenvalue normalized by the length. In 1975, there was an extension of Weinstock's theorem for higher eigenvalues, which was proven by Hirsch, Payne, and Schiffer. And they proved a little more complicated bound on products, but a consequence of their work is that if we take the nth, this is for a simply connected plane domain, if we take the nth Steklov eigenvalue times the length, it's bounded above by 2 pi n. So notice when n is 1, that's exactly the Weinstock bound. Okay, and actually recently in 2008, it was shown by Girard and Polterovich that these bounds are actually sharp. So 2 pi n is the best possible bound. However, they're not achieved except when n is 1. Okay. So when n is 1, of course, it's achieved by the disk. What Girard and Polterovich showed is that they're achieved asymptotically when the simply connected domain degenerates into sort of pinched disks of the same size. So you imagine pinching. So it's sort of achieved by a disjoint union of disks, and you can approximate that if you do it carefully by a simply connected domain. So in particular, although the maximizing problem is achieved for sigma 1, it's not achieved for higher sigma. Okay, and so it turns out. So one of the first things that Fraser and I looked at was the annulus. And I'll describe in part 3 how we were actually explicitly able to find the maximum for the annulus. But the first step in doing that was to study S1 invariant metrics. So on an annulus, of course, there's a family of metrics which have the conformal symmetry, namely they're S1 invariant. So we could write them in conformally flat form. So they're just a function of t times dt squared plus d theta squared. That's the product metric on minus tt cross S1. And then capital T marks the conformal structure on that annulus. Okay, and so we use separation of variables technique, actually somewhat challenging exercise in separation of variables. We were able to show that there's a unique choice of T and a metric G, meaning really the boundary lengths in this case, so that it's maximized. And we studied the geometry of that. So we were able to explicitly construct the maximizer over S1 invariant metrics. Now recently, the question of maximizing higher eigenvalues among S1 invariant metrics. So this doesn't apply to general metrics on the annulus, but for metrics that are S1 invariant, there's an interesting paper that I think appeared about a year ago by Fan, Tam, and Yu. And they proved the following surprising results. They showed that when n is at least 3, so sigma 1 is the one we handled, and they proved that for sigma 3 and above, there is a rotationally symmetric metric which maximizes sigma and L, so a T and a metric. And they gave an explicit description of the optimal geometry. I'll describe those. It's related, again, to this free boundary minimal surface, which I'll describe in a bit. So in particular, the only case for the annulus for which the maximum is not achieved is n equals 2. But of course, that's only among rotationally symmetric metrics. It's not clear that that's the maximum overall metrics. In fact, they for n equals 2, they showed the maximizer does not exist among rotationally symmetric metrics. And they also looked at the problem of maximizing in a given conformal class. So you could fix a t, and then you could try to maximize. And what they showed is that when t is small, smaller than a fixed constant, the maximum sigma 1L over arbitrary metrics, that is metrics that are not S1 invariant, is actually bigger than the maximum over S1 invariant metrics. So they looked at the S1 invariant metric, and they did a perturbation, and they were able to show for t small that sigma 1L actually goes up. So again, that's a bit surprising. It says that assuming the maximum exists, and for fixed t, it is not an S1 invariant metric. And so those were some rather interesting results. So for surfaces, for upper bounds on higher eigenvalues for general surfaces, there were extensions of Hirsch-Payne, the Hirsch-Payne-Schiffer bound by the same pair of authors, Girard and Polterovich. And they proved sort of a generalization of R bound. So this is the sum of the 2 pi times the sum, gamma plus k times n. And this reduces when n equals 1 to the bound that I described. And this bound was improved very recently in a paper that was just posted this year by a bound which is actually linear in n, gamma, and k. This is by Karpukin, who's a student of Polterovich in Montreal. And so there's a much sharper upper bound when n is large, given there. And then the question of whether you could extend the upper bound to higher n so that it's independent of k, the number of boundary components, was considered by Colbois, Elsefi, and Girard. And they proved a coarse estimate of that type. But quite recently, in 2011, Hassanejad proved an upper bound with the correct dependence on n and gamma. So the dependence on n is actually sharp because of the Weil asymptotic estimates that I'll say a little bit about in a minute. And the dependence on gamma is also expected to be sharp for constants a and b. The constants, however, are not so easily computable in the estimate. Okay, and so let me say a bit about Weil asymptotics. So actually, the asymptotic law for Steklov eigenvalues appears also in the old literature. It was done in 1955 by a Swedish mathematician, Sandgren. And what it says is that if we take the jth eigenvalue, the jth Steklov eigenvalue, then it grows like it's 2 pi j divided by just the dimensional constant omega n minus 1, and then the volume of the boundary. This is the volume of boundary omega raised to an appropriate power, and then plus a term that's bounded. And so in particular, the Weil asymptotics in this case would allow you to determine the volume of the boundary. So if you take a, and this works in any dimension. So if you take a manifold with boundary from the Steklov spectrum, you can determine the volume of the boundary. It's not known whether you can compute the volume of the interior, whether it's a spectral invariant. In fact, it's definitely not in 2 dimensions, but even in higher dimensions for domains in R3 or domains in R2, it's not known. However, there's a recent paper which gives an improvement of this in the 2-dimensional case. And so there's a more refined Weil asymptotic formula which exploits the fact the boundary is 1-dimensional. And this is by Girard, Parnowski, Polterovich, and David Schur, who's a former Stanford math graduate student. And they proved that for n equals 2, the spectrum actually determines the number of boundary components and the length of each boundary component. So they were able to refine the asymptotics to calculate a bit more geometric information on the surface from the spectrum. Okay, and so that's that ends my survey. Let's see, when did I start? 2:45, right? Okay, that's a survey of that I wanted to give for the eigenvalue problem. So there's still, I mean, in terms of recovering the geometry of a domain from the spectrum, there's still, very far to go to do anything like that. But there are some recent results. Okay, and so again, I'm going to now come back to the extremal problem just for sigma 1 times the length. And again, the surfaces, let's just take oriented surfaces. So they're classified by the genus, which I'll call gamma, and the number of boundary components, which I'll call k. Okay, and so it's topologically a closed surface of genus gamma with k disks removed. And so Weinstock's theorem says that when gamma is 0, k is 1, the maximizing metric is a flat metric on the unit disk. Okay, and so we looked at the question of what are the maximizing metrics for other topologies. So suppose you take a more general surface with boundary, then can you find a smooth metric that maximizes sigma 1L? And if so, what does it look like? What's the geometry of that? And so actually one of the cases we were able to explicitly resolve is the Annulus case. So there's actually a unique, and there's actually a sort of obvious equivalence for metrics also. But on the Annulus, we were able to explicitly determine the maximum value and the metric that achieves it. And it turns out in that case it's a rotationally symmetric Annulus with boundary circles of equal length. So it's an S1 invariant Annulus. In fact, it's the same, what we showed is it's the same extremal metric that you got when you considered S1 invariant metrics. So we were able to prove the general extremal over all metrics is S1 invariant. Okay, and we also showed that in the genus 0 case, for any number of boundary components, there is a smooth metric which maximizes sigma 1L, and we were able to show that the values of sigma 1L as a function of k are strictly increasing, and they start when k is 1 at 2 pi, and they go and they approach asymptotically 4 pi. So this is 2 pi, which is k equals 1, and then k equals 2 is somewhere up here. It's bigger. There's 4 pi out here. And so we showed that when k increases, these strictly increase, and they approach 4 pi as k goes to infinity. So that's the. So for genus 0, we have, of course, we can't explicitly compute the maximum, but we have a good handle on what the metrics look like, and I'll describe that in a minute. And so, so the way we did it is through a kind of geometric understanding of the extremal metrics. And one of the reasons I'm speaking on it here is because it turns out to be related to minimal surfaces of a certain type. And so let me describe that. Okay, and so there's first of all a general theorem about extremals. So if you assume you have a metric, a smooth metric that maximizes sigma 1L, then the theorem says that the multiplicity of sigma 1 is at least 2. So there are at least 2 independent eigenfunctions. And you can construct a proper map, a proper branched minimal immersion phi from m to the n ball, where n depends on the multiplicity. N is at least 2. And this is an immersion by first eigenfunctions. So phi 1 up to phi n are first eigenfunctions. And moreover, it's a conformal immersion. So it's a minimal harmonic immersion. So it's conformal. And so it's geometrically, the image is a free boundary minimal surface. So the Steklov boundary condition, it turns out to be the condition that the surface meet the sphere orthogonally. So that's the general theorem. And so it's called a free boundary minimal surface. Say more about that in the next slides. And so the extremal metric G is then the induced metric on the surface up to a factor, to a constant factor. And so what it says, it's kind of an amazing thing. It says there's this eigenvalue problem. If you can find extremals, maximize it. Actually, the same theorem is true for higher eigenvalues as well. Then you can, if you can maximize it, then you can arrange eigenfunctions which give you a minimal immersion or a branched minimal immersion to the ball. So the sum of squares is 1 on the boundary, and so that it meets the boundary of the ball orthogonally. So that's the theorem. And actually, in a certain sense, the theorem is not really due to us. There's an analogous theorem for closed surfaces, which is done by Nadarashvili in 1996. And this theorem uses a similar idea, just a modification of that idea. And so let me say a little bit more about free boundary minimal surfaces. So we're interested in proper minimal surfaces in the ball, and the free boundary condition is that they're orthogonal at the boundary. So that means that the co-normal to the surface is the position vector. So we're in the ball. And so the co-normal vector eta is equal to the position vector x at a point. So that's a free boundary minimal surface. So these minimal surfaces come up if you consider sweep outs of the ball by relative cycles, so cycles whose boundary lie on the sphere, and then you look for critical points. They would have to be min-max critical points for area, but the orthogonality condition is just the condition that the area is critical for variations which are not 0 on the boundary but are tangent to the sphere on the boundary. So not only is it natural in this eigenvalue problem, it's also a natural variational problem from the plateau point of view. Okay, and so such minimal surfaces have the property that the coordinate functions are harmonic, and the co-normal, the normal derivative of xi is just xi itself. It just reproduces xi. So this is a picture. So the minimality is h equals 0 is the condition that the coordinate functions are harmonic, and then the orthogonality is the condition that the Steklov boundary condition. Okay? And so there's a very nice geometric interpretation of the Steklov eigenfunctions for this problem. The coordinate functions are always Steklov eigenfunctions for a free boundary minimal surface. Okay, so let me give some examples, and I'm going to enlarge my example list from a couple of years ago. There have been some new constructions. So first of all, there's the flat disk. So if you take a disk through the origin, then of course that's a solution. And there's a uniqueness theorem by Nietzsche from about 1985. He proved that the only simply connected free boundary minimal surface in the 3-ball is in fact the flat disk. Now recently, Fraser and I generalized this to all dimensions. So for those of you who kind of look at the analog between this problem and closed surfaces in SN, this is a place where they differ because if you look at the Nietzsche theorem is analogous to Almgren's theorem about a simply connected minimal surface in S3 being an equator. And the proof is kind of similar. It uses the Hopf differential. However, if you look at minimal S2s in higher dimensional spheres, there are lots and lots of them. There's a very rich theory of those. But it turns out that for the free boundary problem, it's only the flat disk in all dimensions, so in arbitrary codimension. And so again, that follows from the sort of vector-valued version of the Hopf differential. It turns out the free boundary condition gives you more rigidity than you get for the corresponding problem in the sphere. Okay, and then the next, the simplest annular surface is the critical catenoid, and probably everybody knows this. So you take the hyperbolic cosine curve and take a tangent line, a tangent line from the origin, and then you revolve the portion inside the line about the axis, and you produce a portion of the catenoid which is orthogonal to the sphere, and there's a unique such portion. And then you can scale the sphere down to radius 1, and you get what's called the critical catenoid. So that's a free boundary minimal surface which is homeomorphic to an annulus. Okay, and there's an announced construction that hasn't appeared yet by Kapouleas and Lee, where they do a gluing construction to approximate the union of the critical catenoid and the disk by embedded minimal surfaces. So there's a natural immersed surface, which is just you take the critical catenoid, and then you look at the disk through the origin. Then those are surfaces which meet orthogonally on a circle, and then you can ask, is it possible to regularize that, maintaining the free boundary condition? Well, the free boundary condition is an elliptic boundary condition, so in principle it ought to be possible to do that. But like a lot of these gluing theorems, it's hard work, but they have nonetheless announced that construction. So the result is that there exists, for very large genus, there exists high genus minimal embedded free boundary minimal surface of genus gamma for gamma large, and with 3 boundary components. And in fact, the larger gamma is, the closer the boundary components are to circles. So it's a union of, almost a union of 3 circles, the boundary. So let's see. And then is another example that we came up with just from looking at separation of variables on the annulus. This is called the critical Mobius band. And so this is, so if we think of the Mobius band as R cross S1, and we identify, so T is the variable on R and theta on S1, and we do the identification T theta with minus T theta plus pi, then the quotient is a Mobius band. And we constructed, just in very simple form, a minimal embedding of the Mobius band into R4. So it's a proper minimal embedding, so think of it as sort of like the catenoid. Some sense, and then it turns out that there's a unique choice of T naught, so that if we cut it off between minus T naught and T naught, then we get a free boundary surface. Okay, so it's an embedded Mobius band in the ball, which satisfies the free boundary condition. And so in fact, I mention it because it's will be the extremal for the Mobius band. Then let me mention, I mentioned the paper of Fan, Tam, and Yu. So actually in their paper, they construct extremal metrics on the annulus for every eigenvalue bigger than 2, so 3 and above. And each one of those produces a free boundary minimal annulus in the ball. Now, some of them, for some of the eigenvalues, it's just a covering of the critical catenoid. For some other ones, it's a covering of the Mobius band. But for certain of them, you get a sequence, a distinct sequence of free boundary minimal embeddings of the annulus in the 4 ball. And so these are S1 invariant free boundary minimal surfaces in B4. So they're annular surfaces, and I've written the explicit formula there. There's some, again, there's some choice, unique choice T sub n for which those are free boundary minimal surfaces. So a little bit surprising. In the 3 ball, we expect the critical catenoid to be unique under reasonable hypotheses. But in the 4 ball, there actually are infinitely many such embedded annuli, even which are S1 invariant. Of course, there may be a lot more that are not S1 invariant. But let me say, in higher dimensions, there's a recent paper you can find on the archive by Frieden, Julian, and Peter McGrath, which constructs many higher dimensional free boundary minimal hypersurfaces that are invariant under certain group actions. So they studied the sort of groups that leave the product minimal cones. So for example, the cone over the Clifford torus is invariant under certain group action. There similarly are an infinite number of free boundary minimal surfaces in the ball that are smooth ones that are invariant under the same group action. So they studied that question, and I'll let you read it. So there are a lot of those. Let me say there's also a compactness theorem which was done a few years ago by Fraser and Lee, and they showed that the space of embedded free boundary minimal surfaces in B3 and also in 3 manifolds with positive Ricci curvature, non-negative Ricci, with a fixed topology is compact in the C infinity topology. So they showed that there's the area and the maximum curvatures are uniformly bounded, and so there's a compactness theorem, just in the 2-dimensional case, of course. And so a key step in the proof is again by analogy with results for closed minimal surfaces in S3. Is a lower bound on the first Steklov eigenvalue. So again, one might conjecture that for embedded free boundary minimal surfaces, sigma 1 is 1. That would be the analog of Yau's conjecture for closed surfaces in the sphere. And they were able to prove it's bigger than a half. So it's a proof that uses a kind of clever analog of the Choi-Wang result, which gives a lower bound on lambda 1 for closed embedded minimal surfaces in S3, which is also off by a factor of 2. Okay. And so let me describe the main results that we obtained. Let me summarize them. And we haven't gone much further with these than we had a year or two ago. And maybe I'll explain a little bit what the difficulties are. So the main theorem about the annulus case is going to be that the maximizer is uniquely achieved by the critical catenoid for the annulus. And so that characterizes the maximizing metric. And so in order to do that, we had to prove a characterization of the critical catenoid. And so I call this theorem A. So it says, assume we have a free boundary minimal annulus in Bn, it could be in any dimension, and assume that the coordinate functions are first eigenfunctions. So it doesn't have to be embedded or anything, but the coordinate functions are first eigenfunctions. Then in fact, n is 3 and sigma is the critical catenoid. So in particular, we're able to prove that the surface is S1 invariant. Once it's S1 invariant, using separation of variables, you can analyze the situation pretty well. But the key thing here is the S1 invariance. And that follows from the condition sigma 1 is 1. And of course, that's well, expected to be a necessary condition. I'm not really sure if we know a non-S1 invariant. But for example, the annuli in B4 I mentioned by Tam and his co-authors, those are embedded, the coordinate functions are nth eigenfunctions, right? They're embedded by the nth eigenfunction, where n is bigger than 3, bigger than or equal to 3. Okay, so the condition that sigma 1 is 1 is a rather special assumption. And there's a similar corresponding result for the Mobius band. So if we assume we have a free boundary minimal Mobius band in Bn, and such that the coordinate functions are first eigenfunctions, then in fact n is 4 and it's the critical Mobius band. Okay, so in particular, that tells us that if we can construct a maximizer for the first sigma 1 times L, then we'll be able to say what it is. We'll be able to explicitly identify it. And so And so for higher gamma and k, well, really for higher k, we can define a number, sigma star, which is the sup, sigma 1L over all smooth metrics. And then we can ask whether it's achieved. And so the Weinstock theorem says this is 2 pi. And then for sigma star of 0, 2, that's the annulus. We then show that sigma 1L is bounded by that of the critical catenoid. And so that number you can compute, or you can approximate anyway. It's a transcendental number. But it's approximately 4 pi over 1.2. So it's bigger than 2 pi and less than 4 pi. So that's the critical catenoid. And now for genus 0 and k boundary components, we're able to construct a maximizing metric for any k. And we can show that these numbers are strictly increasing. So when you increase k, sigma star of 0k strictly increases, which is an important part of the proof, actually, and the existence proof. And so for each k, there's a maximizing metric. And sigma k's, the sigma k's are metrics, they're minimal surfaces in B3, and their areas are bounded by 2 pi. So the area is less than 2 pi. And the limit is actually a double disk. So the limiting area is exactly 2 pi. And so these look like the following. Actually, a good way to visualize these surfaces is to so the computer-generated picture there has nothing to do with the actual surfaces. We just got somebody to draw something that looks sort of. So they're like 2 disks with a lot of little boundary components. So the way to think of it is if you take S2 and you take an equator, and then you drill a lot of holes out around the equator. So you remove k small disks around the equator, and then you take it and you let out the air. You push down, you shove down the upper hemisphere to approximately a plane and the lower half to about a plane, and then you get that's what the surface is supposed to look like. So that's my terrible hand-drawn sketch. This is a computer rendition which doesn't look anything like the real surfaces, but that's the basic. The basic features are that the areas are strictly less than 2 pi, but asymptotic to 2 pi. The surfaces converge in the interior to a double disk, and the areas converge also to twice the area of a disk, and the areas are strictly increasing. So that's the picture. So in particular, it gives the existence of an embedded free boundary minimal surface for any genus 0 with any number of boundary components. Now actually, I should say for large numbers of boundary components, these were also, and even with genus 1, there's a paper recently by Frank Picard and co-authors in which they construct surfaces that look roughly like this by gluing methods. And so most likely they're the same surfaces, but it's very difficult to prove that. And also we get one for every k, of course. Whereas the gluing methods only give it for k large. Okay, and so the idea of the proof is to prove a kind of hard existence theorem. So this is very different from the proof of Weinstock's theorem. So Weinstock's theorem, all we had to do was exhibit a conformal map to the disk, and then we could directly prove the estimate, the sharp estimate. Now that just simply doesn't work even for annuli. Well, we found actually if you take annuli with T large, there is an easy proof that the critical catenoid, we called them supercritical annuli. In the first paper, there's an easy proof. But for T small, it's much more subtle. And in fact, the paper by Tam and his co-authors shows that when T is small, the maximizer needn't even be rotationally symmetric. Needn't be S1 invariant. So the problem is a lot harder. And I doubt if there's any way to do it without actually proving the existence. So the theorem says that if you take k bigger than or equal to 1 and genus 0 with k boundary components, then there is a smooth metric which maximizes, which achieves the maximum. And so very roughly, you're looking for you're trying to prove convergence of a maximizing sequence of metrics on a surface. And so the natural thing to do is to separate the conformal structure from the metric itself in the conformal class. And so you have to first control the conformal structure, and then once you know the conformal structure doesn't degenerate, then you can study metrics in in a fixed or a compact set of conformal classes, and it's possible to do that. It's not a very easy theorem, though. Okay, and so once we have the existence theorem, then the fact that the critical catenoid achieves the maximum, the thing I called theorem 1, it then follows from these 3 steps. So you first assert the existence of a metric which achieves the maximum, and then we use the characterization. Well, actually, the first 2 steps are sort of embedded together because the existence proof also involves characterizing the maximizing metrics for an approximate problem. But anyway, the characterization tells us that maximizing metric arises from a free boundary minimal immersion in the ball by first eigenfunctions, and then because of the uniqueness theorem, so this would be an annulus embedded by or immersed by first eigenfunctions, and so we then prove that that's the critical catenoid. So those are the 3 steps involved in that. Okay, and the limit, to understand the limiting behavior as k goes to infinity, there's a certain aspect of the geometry of these that comes out of the fact that the first eigenfunctions are, the first sigma 1 is 1. And so notice that if we draw the critical catenoid, I have it here, notice it has the property that it's star-shaped. So if I take the origin here and I take any ray from the origin, it hits the surface in at most 1 point. So there's one ray that touches on the boundary and then some rays that miss it. But it turns out that property, the fact that the surface is star-shaped, is a consequence in the genus 0 case of sigma 1 being 1. And so so we can interpret sigma 1 as 1 tells us something about nodal sets of first eigenfunctions. But in this case, the first eigenfunctions are simply the intersections of the surface. They're the coordinate functions. And so the nodal set is the intersection of a plane through the origin with the surface. Okay, and so the fact, because of genus 0, you can show that the nodal sets don't have any, the nodal curves don't have any singularities in the interior of the surface. Using that property, you can show the surface is actually star-shaped. So that's the basic geometric property. Now, unfortunately, that argument, of course, doesn't work for higher genus. The nodal sets could be substantially more complicated. Okay, and then the fact that we had, so remember we had an upper bound on sigma 1 times L depending only on the genus, right? So in particular, that upper bound, that coarse upper bound turns out to be 4 pi in this case, genus 0 and k boundary components. So in particular, the area is bounded by 4 pi, and it's star-shaped, so they're stable inside. So they're star-shaped, so the function x dot nu, the support function, is positive, and so the surfaces are stable and they have bounded areas. So that gives us uniform curvature estimates inside, and so we get uniform. We get a compactness theorem interior to the disk, and then we also have to then understand the limits, the limit of these. So there's a limit which is smooth in the interior, and there's a limiting surface sigma infinity, possibly with multiplicity. And then we have to show the limit actually has multiplicity exactly 2. And so there's some work involved in that. But it can't be more than 2 because they're star-shaped. And so the fact that it actually converges to something with multiplicity takes a little bit of work. But we can analyze that, and then so the origin lies in the limiting surface, so it's a cone, and then it has to be a flat disk with multiplicity 2. And then there's a separate argument to show the areas converge. You also have to show that there's no concentration of area along the boundary. So it might happen that the area drops in the limit. But that follows from a kind of boundary monotonicity formula. You can estimate the area in a sharp way and show that there's no area concentration on the set where the curvature is large. Okay, and so the areas converge. Let's see, and then so that finishes the argument. So sigma star is then sigma 1 times the boundary length. So sigma 1 we know is so sigma 1 times. So we've normalized. sigma 1 to be 1 because we're in the unit ball. That's that normalization. And then for a free boundary minimal surface, you can compute the length of the boundary volume in terms of the interior volume. And for two-dimensional surfaces, it's like the standard disk. The boundary length is twice the area inside 2a sigma. And so the areas converge to 2 pi, and so the sigma star converges to 4 pi, and they're strictly increasing. Okay, and for the Mobius band, the steps are pretty much the same as for the annulus surface, and so it turns out that sigma 1, the critical value for the Mobius band, turns out to be that. You can actually explicitly compute it. And so if we take any metric on the Mobius band, then sigma 1L is bounded above by that number, and equality if and only if m is equivalent to the critical Mobius band. And again, the proofs are to sort of, by a general argument, construct a maximizer on the Mobius band, and then use the characterization to say that it comes from a minimal immersion, a free boundary minimal immersion into the ball, and then we use the uniqueness result. It's congruent to the critical Mobius band. In this case, it lies in the 4 ball. Okay, so those are the results we have, and that's my last slide. But let me just say, of course, there are more things one would like to do. And in particular, it would be nice to be able to do this for higher genus. And so far that hasn't worked somehow. You need a theorem that says that when you add a handle, so if you take a disk, for example, and add a handle, then you need to know that the supremum actually goes up when you do that. And well, recently I've actually been able to do something like that for closed surfaces. In fact, I talked about it in Schoen. I actually don't know how to do it in this case. The Steklov problem is somewhat different because it doesn't depend on the metric in the interior. It only depends on the conformal structure. So that's what's missing. If it were possible to do that, then I think we could solve the extremal problem for any genus and any number of boundary components. But as I say, so far that's been problematic. So, okay, so again, happy birthday, Harold, and I think I'll stop there then.